Welcome to this walkthrough of LeetCode problem number 1086, titled High 5. In this problem, we'll explore how to compute the average of the top 5 scores for each student from a given dataset of scores. Let's dive in and break it down step by step. In this problem, we are given a list of student records, where each record is represented as a pair, ID, score. The ID represents the student's unique identifier, and the score represents the marks they received on a test. Our task is to write a function that calculates the average of the top 5 scores for each student. The output should be a list of pairs, ID, average, where ID is the student's ID and average is the floor of the average of their top 5 scores. The result list must be sorted in increasing order of student IDs. The input will be provided as a list of lists, where each inner list contains an ID and a score, and the output will also be a list of lists, where each inner list contains the ID and the corresponding floored average of the top 5 scores. To better understand the problem, let's look at an example. Suppose the input is items equals 191, 192, 293, 297, 160, 277, 165, 187, 1100, 2100, 276. Here, we have scores for two students, 1 and 2. For student 1, their scores are 91, 92, 60, 65, 87, 100. Out of these, the top 5 scores are 100, 92, 91, 87, 65. When we calculate the average of these top 5 scores, we get 100 plus 92 plus 91 plus 87 plus 65, //5, which equals 87. Similarly, for student 2, their scores are 93, 97, 77, 100, 76. The top 5 scores for student 2 are 100, 97, 93, 77, 76, and the average of these scores is 100 plus 97 plus 93 plus 77 plus 76, //5, which equals 88. Finally, we return the results as a list of pairs, sorted by the student IDs 1, 87, 2, 88. Now, let's consider another example. If the input is items equals 1100, 785, 781, 199, 770, 790, 192, 189, 195, 788, 793, we have scores for students 1 and 7. For student 1, their scores are 100, 99, 92, 89, 95. Out of these, the top 5 scores are 100, 99, 95, 92, 89. The average of these scores is 100 plus 99 plus 95 plus 92 plus 89, //5, which equals 95. For student 7, their scores are 85, 81, 70, 90, 88, 93. From these, the top 5 scores are 93, 90, 88, 85, 81, and the average of these scores is 93 plus 90 plus 88 plus 85 plus 81, //5, which equals 89. Once again, we return the results sorted by the student IDs 1, 95, 7, 89. The problem also comes with several constraints and edge cases to consider. For example, the constraints specify that each student will always have at least 5 scores, and the input size can be as large as 10^4. One edge case is when the input contains only 5 scores for a single student. For instance, if items equals 150, 160, 170, 180, 190, then the output would simply be 170, as all the scores are used to calculate the average. Another edge case involves multiple students, where their scores might be provided in varying orders. Additionally, we need to ensure the solution handles cases where the scores for a student are already presorted in descending order, as well as scenarios involving large input sizes to verify that the function remains efficient. Let's look at one more edge case. If the input is items equals 290, 1100, 180, 295, 185, 285, 170, 280, 175, 275, we need to calculate the top 5 averages for students 1 and 2. For student 1, their scores are 100, 80, 85, 70, 75, and the average of their top 5 scores is 100 plus 85 plus 80 plus 75 plus 70, //5, which equals 85. For student 2, their scores are 90, 95, 85, 80, 75, and the average is also 95 plus 90 plus 85 plus 80 plus 75, // 5, which equals 85. The final output is 1, 85, 2, 85. By considering these constraints and edge cases, we ensure the solution is robust and handles all scenarios efficiently. To start, let's consider a brute force approach to solve this problem. The intuition behind this method is straightforward. For each unique student ID, we extract all their scores, sort them in descending order, pick the top 5, and calculate their average. While this might seem simple, it involves significant computational overhead. Specifically, for each student, we need to filter through the list to collect their scores, which takes n time, and then sort those scores, which adds k log k, complexity, where k is the number of scores for that student. When this process is repeated for every student, the overall time complexity becomes n squared, in the worst case. Additionally, we need extra space to store the scores for each student, resulting in an n space complexity. This approach is not practical for large datasets because it relies on repeated filtering and sorting operations, making it computationally expensive and inefficient for scaling with more data. Now, an optimized approach involves leveraging a min-heap, or priority queue, to efficiently manage the top 5 scores for each student. First, we group all the scores by student ID using a dictionary, which allows us to quickly access the scores for each student. For each student's scores, we use a min-heap to maintain only the top 5 scores. The heap structure ensures that the smallest score is always at the root, and if the heap size exceeds 5, the smallest score is discarded automatically. After collecting the top 5 scores for each student, we compute their average and store the results. Finally, these averages are returned, sorted by student ID. The efficiency of this method lies in how it handles the scores. Grouping by student ID takes linear time, and maintaining a heap of size 5 for each record has a constant log 5 time complexity. Overall, this approach runs in approximately n time, with space complexity proportional to the number of unique students, making it both time efficient and memory efficient. This optimized approach is highly effective for several reasons. First, it scales well with large datasets since it avoids the repeated filtering and sorting operations of the brute force method. By using a heap, we limit memory usage to just the top 5 scores per student, which is especially important when dealing with a massive number of records. While there are alternative approaches, they have notable trade-offs. For example, directly sorting each student's scores and then picking the top 5 is simpler conceptually, but the sorting step introduces higher computational costs, especially when there are many scores per student. Another option is counting sort, which can be faster if the score values are within a fixed range, like 0 to 100, but this method requires additional space for the score range and lacks flexibility if the scores fall outside this range. Overall, the heap-based method provides a balanced solution with minimal trade-offs, making it the most practical choice for this problem. The heap-based strategy was ultimately chosen because it strikes the best balance between time efficiency, space efficiency, and flexibility. By leveraging a min-heap, we ensure that only the top 5 scores for each student are stored, avoiding the need to sort large lists repeatedly. This makes the approach highly scalable, even with large datasets. While alternatives like counting sort may perform better under specific conditions, such as fixed score ranges, they lack the versatility needed for arbitrary score values. Similarly, sorting-based methods in brute force approaches are less efficient due to their higher computational overhead. Comparatively, the heap-based method avoids unnecessary operations like repeatedly filtering or sorting full lists, ensuring that it is robust and adaptable to varying input sizes. This combination of flexibility, efficiency, and scalability makes the heap-based approach the most effective solution to the problem. To solve the high 5 problem, we start by understanding the input and desired output. The input is a list of pairs, where each pair contains a student underscore ID and a score. Our goal is to calculate the average of the top 5 scores for each unique student ID. If a student has fewer than 5 scores, we calculate the average of all their scores. The output is a list of pairs, where each pair contains the student underscore ID and the calculated top 5 average. To achieve this, we need an efficient approach. First, we use a hash map to group the scores by student underscore ID. In this hash map, the keys represent the student underscore ID and the values are lists of scores for that student. As we iterate through the input list, we append each score to the corresponding entry in the hash map. For example, if the input is 1, 95, 1, 85, 1, 75, 2, 100, 2, 80, our hash map would look like this: 1, 95, 85, 75, 2, 100, 80. This grouping step ensures that scores for each student are efficiently organized for further processing. Once we have grouped the scores by student_ID, the next step is to sort the scores for each student in descending order. This makes it easy to access the highest scores. For example, after sorting, the hash map remains 1, 95, 85, 75, 2, 180, but now the scores are already in descending order for each student. After sorting, we calculate the average of the top 5 scores. If a student has 5 or more scores, we sum the first 5 scores and divide by 5. If a student has fewer than 5 scores, we calculate the average of all their scores. The result for each student is stored as a pair in the output list. For instance, with the given example, the top 5 average for student_ID1 is 95 plus 85 plus 75, /3 equals 85.0, and for student_ID2, it is 100 plus 80, /2 equals 90.0. This gives us the final output, 1, 85.0, 2, 90.0. Now, let's consider some edge cases that the algorithm needs to handle. First, if a student has fewer than 5 scores, we calculate the average of the scores they do have. Second, when multiple students have overlapping scores, the grouping step ensures that scores are correctly associated with their respective student_ID. Finally, if the input list is empty, we simply return an empty list as the output. When analyzing the algorithm's complexity, the grouping step, which involves iterating over the input, takes O(n), where n is the total number of scores. Sorting the scores for each student takes O(k*log k), where k is the number of scores per student. In the worst case, this becomes O(n*log n) for all students. Calculating averages for the top 5 scores is linear, taking O(n). Therefore, the overall time complexity is dominated by the sorting step, resulting in O(n*log n). To optimize the algorithm, we can use a min-heap instead of sorting all the scores for each student. A min-heap allows us to maintain only the top 5 scores for each student as we iterate through their scores. This reduces the sorting complexity to OK*log 5, which simplifies to OK, since log 5 is constant. With this optimization, the grouping step remains O(n), maintaining the top 5 scores also becomes O(n), and calculating averages remains O(n). Thus, the overall time complexity is reduced to O(n). Using a hash map to group scores ensures efficient lookups and avoids redundant iterations. This optimization not only improves the algorithm's efficiency but also makes it scalable for larger inputs while handling edge cases like fewer than 5 scores seamlessly. This solution effectively calculates the average of the top 5 scores for each student in a list of scores. Let's break it down step by step. 1. Imports and setup. The default dict from collections is used to store scores for each student in a way that automatically initializes an empty list for new student IDs. The Heap module is employed to maintain a min-heap, which helps efficiently manage the top 5 scores. 2. Processing scores. For each pair, student_ID score, the score is added to the heap, using heap.heapPush. If the heap grows larger than 5, the smallest score is removed using heap.heapPop. This ensures that only the top 5 scores for each student are kept in the heap. 3. Sorting and averaging. After processing all scores, the student IDs are sorted. For each student, the top 5 scores are summed, and their integer average is calculated using floor division, //. The result for each student is appended to the output list in the format student_ID, top_5_average. For output, finally, the list of results is returned, containing the calculated averages for all students, sorted by their IDs. This approach ensures efficiency by maintaining only the top 5 scores for each student during processing, avoiding unnecessary storage of extra data. The solution is optimal for large datasets and adheres to the problem constraints. Here, we start by importing the necessary libraries and defining our solution class. The method Hi5 takes a 2D array called items, where each subarray contains a student ID and their corresponding score. To efficiently manage and calculate the top 5 scores for each student, we use a tree map. This ensures that the student IDs are automatically sorted in ascending order. The tree map stores a priority queue for each student ID. The priority queue is used as a min-heap to keep track of the top 5 scores for that student. Next, we iterate through each pair in the items array. For every student ID and score, we check if the student already has a priority queue in the tree map. If not, we initialize a new one. Then, we add the score to the priority queue. To ensure that we only keep the top 5 scores, we check the size of the priority queue. If it exceeds 5, we remove the smallest score by calling poll. This allows us to maintain only the highest 5 scores efficiently while processing the input data. Now, we calculate the average of the top 5 scores for each student. Using the tree map's entry set, we loop through each student ID and its corresponding priority queue of top scores. For every priority queue, we compute the sum of the scores it contains. Then, we divide this sum by the size of the priority queue, which is always 5 since we ensured that earlier. This gives us the average of the top 5 scores for that student. We then add the student ID and their calculated average as a new array to the result list. Once we have processed all the students, we convert the result list to a 2D array using the toArray method and return it. This completes the solution, ensuring that we efficiently compute the required averages and return them in the expected format. We start with the input list of student scores, where each subarray contains a student ID and their corresponding score. The goal is to compute the average of the top 5 scores for each student. First, we initialize a dictionary called scores using defaultIct list. This will allow us to map each student ID to a list of their scores, which we manage as a min-heap to efficiently track the top 5 scores. Now, we process each score in the input. For the pair 1, 91, we add 91 to the list for student 1, resulting in scores equals 1, 91. Similarly, for 1, 92, the score 92 is added, giving us scores equals 1, 91, 92. For student 2, we begin by adding 93, resulting in scores equals 1, 91, 92, 2, 93. As more scores are added for both students, we ensure that the lists remain sorted as min-heaps. For instance, when adding 100 for student 2, their list becomes 93, 97, 98, 99, 100. Similarly, student 1's scores reach 58, 60, 91, 92, 100 after processing all their input. This setup prepares us to calculate the top averages for each student. Once the scores are organized, we compute the average of the top 5 scores for each student. For student 1, their top scores are 58, 60, 91, 92, 100. Adding these together and dividing by 5 gives an average of 80. We append the result, 1, 80, to our output list. Similarly, for student 2, the top scores are 93, 97, 98, 99, 100. Calculating the average of these values results in 97, so we append 2, 97 to the result. The final output for this example is 1, 80, 2, 97. Now, let's look at another example where a single student has more than 5 scores. Here, the input consists of scores for student 1 only. As before, we initialize a defaultIct to store the scores. For this input, we process each score while ensuring we maintain only the top 5 scores for student 1. Adding 80, 85, 90, 95, and 100 builds the list incrementally until it becomes 80, 85, 90, 95, 100. When we add additional scores like 70 or 60, we first insert the new score and then remove the smallest value to maintain the top 5. For example, adding 70 results in removing the smallest score, so the list remains 80, 85, 90, 95, 100. The same happens when adding 60. Once all scores are processed, we compute the average of the top scores 80, 85, 90, 95, 100. The sum of these values is 450, and dividing by 5 gives an average of 90. We append 190 to our results. The final output for this example is 190. Next, let's explore an edge case where all scores are tied. In this edge case, the input consists of 6 scores of 54 student 1. As before, we initialize scores as a defaultIct and process each score while maintaining the top 5. Adding the first 5 scores results in 50, 50, 50, 50, 50. When the 6th score is added, we insert it into the list and then remove the smallest value, which is also 50. Thus, the list remains unchanged at 50, 50, 50, 50, 50. To compute the average, we sum the top scores, which is 250, and divide by 5 to get an average of 50. We append 150 to our results. The final output for this case is 150. This example highlights how the solution handles scenarios with tied scores while maintaining the constraints of the top 5 scores for each student. To analyze the time complexity of our solution, we can break it down into 2 main steps: processing the input scores and calculating the averages. First, when processing the input scores, we use a min heap for each student to keep track of their top 5 scores. For every score in the input list, we perform a heap.heap push operation to insert the score into the heap associated with the student ID. Since the heap size is capped at 5, each heap push operation effectively takes constant time, 1. If the heap exceeds 5 elements, we remove the smallest element using heap.heap_pop, which also takes constant time due to the size limit. Given that there are n scores to process, this step takes n in total. Next, we calculate the averages for each student. Once the scores are processed, we iterate over the sorted list of unique student IDs. If there are m unique students, sorting these IDs takes m log m. For each student, we calculate the average of their top 5 scores. Since each heap contains at most 5 scores, summing these scores and dividing by their count takes constant time, 1. Therefore, iterating through all m students and calculating their averages requires m time. Combining these, the first step of processing scores takes n, and the second step of calculating averages takes m log m plus m. The total time complexity of the solution is thus n plus m log m. Now, let's analyze the space complexity of the solution. The space usage comes from 3 main components. First, we use a dictionary to store the min heaps associated with each student ID. Since each heap stores at most 5 scores, and there are m unique students, the total space used by the min heaps is 5*m, which simplifies to m. Second, the result list, which stores the final averages for each student, requires m space as well, because it contains 1 entry per student. Finally, the input list itself requires n space. These 3 components contribute to the total space complexity of n plus m. Combining all space considerations, we have m space for the min heaps, m space for the result list, and n space for the input list, resulting in an overall space complexity of n plus m. When compared to a brute force approach, the optimized solution is clearly more efficient. The naive method would involve sorting the entire input list by student ID and score, which takes n log n time, followed by grouping scores and calculating averages, leading to a total time complexity of n log n plus n. Its space complexity is n. In contrast, the optimized solution achieves a time complexity of n plus m log m, and the same space complexity of n plus m, making it better suited for larger datasets. Although both the brute force and optimized solutions share a similar space complexity, the optimized approach is significantly faster because it avoids sorting the entire list of scores. Instead, it sorts only the student IDs, which is particularly beneficial when the number of students, m, is much smaller than the number of scores, n. Considering different scenarios, in the best case, where all scores are unique and m equals n, the time complexity is n plus n log n. In the average case, where scores are evenly distributed among students, the time complexity remains n plus m log m, where m is much smaller than n. In the worst case, if all scores belong to a single student, m equals 1, and the time complexity becomes n. This demonstrates that the optimized solution performs well across all cases, adapting effectively to the distribution of scores and students. When working on this problem, there are some common mistakes to watch out for. First, avoid sorting the entire dataset of scores globally. While it might seem like a straightforward approach, this is inefficient as it increases the time complexity to n asterisk log n, which can be problematic for larger datasets. Instead, it's more efficient to group the scores by student ID and process them individually. Another mistake is not handling ties correctly. For example, if you have scores like 90, 90, 80, 70, and 60, skipping a tied score might result in an incomplete top 5. Be mindful of this and ensure tied scores are accounted for properly. Lastly, storing all scores for each student in memory can lead to excessive memory usage. A better approach is to use a min-heap or a fixed-size list to dynamically maintain only the top 5 scores for each student, reducing memory overhead significantly. Now, let's look at a few more pitfalls. Using nested loops for a brute force solution is another inefficient approach. Iterating through the dataset multiple times can lead to a time complexity of n squared, which is unsuitable for larger datasets. A more optimal solution is to use a single pass with a hash map to group scores by student in a heap or sorted structure to maintain their top scores, improving efficiency. Additionally, not validating the input properly can lead to runtime errors. For instance, assuming all student IDs or scores are valid integers without checking input constraints might cause issues. Always include validation checks to handle edge cases like empty inputs, non-integer values, or missing fields to ensure your solution is robust. In interviews, it's important to recognize key patterns that are often associated with problems like this. Many top K element or percentile-based problems can be solved efficiently with heaps. For example, a min-heap is perfect for maintaining the smallest of the largest scores, such as the top 5 in this case. However, while heaps are efficient, with a time complexity of O log k per insertion, they do add some implementation complexity. For smaller datasets, it might be quicker and simpler to sort the scores for each student instead. When working through the problem, always ask clarifying questions about constraints, such as the maximum number of scores per student or whether scores are guaranteed to be unique. Be prepared to handle edge cases like students with no scores, fewer than 5 scores, all scores being the same, or an extremely large dataset. This problem shares similarities with several other LeetCode challenges that are worth studying. For instance, LeetCode 347, Top K Frequent Elements, involves maintaining the top K elements efficiently. LeetCode 703, KTH Largest Element in a Stream, demonstrates using a min-heap to dynamically track the kth largest element, which is very relevant here. LeetCode 295, Find Median from Data Stream, offers a more advanced use case of heaps for maintaining running statistics. Additionally, LeetCode 973, K Closest Points to Origin, provides another example of efficiently selecting K elements using heaps. When considering alternative approaches, brute force is straightforward but inefficient, with a time complexity of n squared. It's only suitable for small datasets where clarity and simplicity outweigh performance. Using a hash map combined with sorting is another viable option, with a complexity of n asterisk log k. This approach is easier to implement but less memory efficient compared to a heap-based solution. The most efficient approach for this problem combines a hash map with a min-heap. By grouping scores using a hash map and dynamically maintaining the top 5 scores with a min-heap, you achieve a time complexity of n asterisk log 5, which simplifies to n. This method is highly efficient for large datasets and avoids unnecessary overhead from storing or sorting all scores. The trade-off is a slightly higher implementation complexity compared to simpler methods, but the performance benefits make it worthwhile for scaling to larger inputs. Overall, this solution strikes the best balance between efficiency and practicality, especially when working with large or dynamic datasets. Thank you for following along. Today, we explored how to solve the high 5 problem using hash maps and min-heaps. Remember the key takeaways about efficient data structures like hash maps for grouping and heaps for priority-based retrieval. If you enjoyed this, don't forget to like and subscribe for more tutorials. Keep practicing, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!